Hello everyone, and welcome to our session on the sliding window technique. Today, we'll explore this powerful method used to optimize algorithms, especially for array and string problems. We'll cover its definition, discuss its importance, and highlight high-level applications such as substring search and maximum sum subarrays. Let's dive in. Let's start with the definition. The sliding window technique is a method used to reduce time complexity when processing sequential data. It involves maintaining a window, a subset of contiguous elements, that slides over the data one element at a time. This approach is particularly effective for problems where elements need to be processed continuously. Key characteristics include maintaining a current set of elements, the window, dynamically updating the window by adding new elements and removing old ones, often transforming an O(n) squared brute force solution into an O(n) solution. Now, let's look at the core concepts and strategy behind the sliding window. Fixed window size. Here, the window remains a constant size, such as examining every subarray or substring of a fixed length k. Dynamic window size. Alternatively, the window size can change based on problem constraints, like finding the smallest subarray that meets a certain condition. The typical process involves initializing window pointers, usually start and end indices, sliding the window across the data while updating cumulative values, for example, sum or frequency counts, and checking if the current window meets certain conditions, adjusting window boundaries as needed to optimize the solution. This process allows us to efficiently compute the desired results with minimal recomputation. To see this in action, let's go to the Visual Studio Code and write code for sliding window technique. I am into Visual Studio Code. I am first going to create two demonstration functions that implement the sliding window technique to solve problems on arrays efficiently, one using a fixed window size and the other using a dynamic window size. For the fixed sliding window example, I create a function called maxSubarraySumFixedWindow that accepts an array and a window size k. The goal here is to calculate the maximum sum of any contiguous subarray of size k. In this function, I start by computing the sum of the first k elements, which forms our initial window. Then, I slide the window across the array by adding the next element and subtracting the element that is no longer in the window. This way, I update the window sum in constant time for each iteration. I keep track of the maximum sum encountered, which allows the algorithm to run in O(n) time, a significant improvement over a brute force approach. For the dynamic sliding window example, I create a function called minSubarrayLength that accepts a target sum and an array. The goal here is to find the minimum length of any contiguous subarray whose sum is at least equal to the target. I begin by initializing a window sum to 0 and set a left pointer at the start of the array. As I iterate through the array with a right pointer, I add the current element to the window sum, expanding the window. When the window sum becomes greater than or equal to the target, I then try to shrink the window from the left by subtracting the element at the left pointer and moving left forward, all while keeping track of the smallest window length that satisfies the condition. This process efficiently adjusts the window size dynamically in O(n) time. In the main function, I define example arrays and corresponding parameters for both scenarios. For the fixed window demonstration, I specify an array and a window size, then print the maximum sum of any subarray of that size. For the dynamic window demonstration, I specify another array and a target sum, then print the minimum subarray length that meets or exceeds the target. This overall demonstration illustrates the core concepts of both fixed and dynamic sliding window techniques, highlighting their efficiency and simplicity in solving array-based problems. Now let's run it. And here you will find it has returned the output. Now let's go back to presentation. Let's analyze the performance and consider practical applications. Time complexity. For a fixed window, the time complexity is O(n) because each element is processed once. For a dynamic window, the complexity is generally O(n) as well, though worst-case scenarios might vary slightly based on specific implementations. Practical applications. In substring problems, such as finding the longest substring without repeating characters. For array problems, like finding the maximum or minimum sum subarrays. In data stream analysis, where you need real-time processing of streaming data for analytics. These examples demonstrate how the sliding window technique is applied in real-world scenarios. To wrap up, the sliding window technique offers significant performance improvements by maintaining and updating a subset of data with minimal recomputation. It can be applied with fixed or dynamic window sizes, depending on the problem at hand. Visual tools like animations help clarify how the window moves and how efficiency gains are achieved. Before we move into our Q&A session, I'd like to emphasize the key takeaways: understanding when to apply fixed versus dynamic window approaches and weighing the trade-offs between time complexity and space utilization. Now, I welcome any questions or discussion on the sliding window technique. You can post your question in comment section. Thank you for your attention. See you in the next session.